We rely on metals to perform in the most demanding environments and under incredible stresses and strains. Metals are often engineered to the demands of their applications. That can make them softer, brittle, harder, or corrosion resistant. The way a metal performs is closely linked to the composition of the metal. The elemental composition of metals used in products we produce is critical to meeting these varying demands. Optical Emission Spectrometry, or OES, is a key technology to ensuring that the right elements are present in the proper concentrations, as well as ensuring that unwanted elements are not present. But what is OES and how does it work? Optical Emission Spectrometry is a fast, accurate, and reliable method for determining the full elemental composition of metal alloys. A sample is placed on the spark stand of the spectrometer. With the sample in place, the chamber is flooded with argon gas. The argon serves several purposes. First of all, it purges the ambient air and provides a known atmosphere for taking the reading. It also protects the sample surface as it becomes ablated during the process. And finally, it initiates the reaction required to analyze the sample. A high-energy spark is sent from the electrode toward the conductive metal sample. This discharge ionizes the gas and creates an argon plasma with free electrons. Powered by the high-voltage pulse, the charged particles slam into the sample surface and ablate the metal atoms. When this collision happens, the valence shell electrons of the atom move into a higher energy state and then fall back. As they fall back into a lower state, energy in the form of a photon is released. The photon is a wavelength that is equal to the specific energy difference between the higher and lower level energy state. The emitted light of all of these photons is directed via a direct view slit or optical fiber into the optical system. The light strikes a grating surface which disperses or separates the white light into a spectrum. The light we see with our eye is a very narrow portion of the overall electromagnetic spectrum. A wide portion of the specific energy in these plasmas exists in the spectrum's visible, ultraviolet regions, and even vacuum UV region. This is another reason that argon gas is used. Ambient air would actually absorb the photons in the UV vacuum region. The most sensitive OES instruments will create a vacuum state in the optical system. Many more economical and benchtop systems will choose to use an argon purge. Sensitive detectors are positioned within the optical system to capture specific photons within the electromagnetic spectrum. When a photon strikes the specific detector, the presence of an element can be determined. The amount of energy striking the detector enables the spectrometer to determine the quantity of that material. OES instruments are often subjected to extreme and volatile environments. Quantification is only possible with a well-calibrated instrument in a stable environment. A well-designed instrument will include features such as thermal isolation and rigorous internal fixturing. Samples with known concentrations of specific elements are used to create calibration curves. Once these calibrations are made, they remain stable for a long period of time. The measurement from the sample can be compared to these calibration curves to determine the exact quantity of each element. With few moving parts and wear components, optical emission spectrometers can withstand the rigors of industrial applications for a very long time with little or no issues. The key factors in selecting a spectrometer for your application relies primarily on the speed, precision, and accuracy of the system, paired closely with user-friendly software and knowledgeable support from the manufacturer. Having all of these characteristics in your instrument will ensure that the metals you produce or work with are of the highest quality possible and that you can get them to market quickly and efficiently.